Hello and welcome. My name is Brenda Davison. This is SFU Math152. We are going to cover today section 5.4, indefinite integrals. So the key difference between what we did last lecture is this IN here. So last time we were looking at the definite integral. Today we're going to take a look at the indefinite integral. Last lecture was a big moment. Actually, we saw the fundamental theorem of calculus, a key result in calculus. And here is the part 2 of that theorem. And that is, if f is continuous on a closed interval a, b, then the definite integral, this is the definite integral because we have endpoints here, the definite integral from a to b of f of x dx is the antiderivative, any antiderivative of little f, capital F, evaluated at the upper endpoint, subtract the same function evaluated at the lower endpoint. Okay, we have the capital F prime is equal to f. So in order to be able to evaluate an integral, we need a way to find the antiderivative, capital F, of the given function, little f. And so what we're going to talk about for the next little while is how we go about finding those antiderivatives. So let's just make a note in our head of what is important here, and that is both parts of the fundamental theorem of calculus establish a connection between the derivative and the definite integral. This is an amazingly important result. Okay, so let us take a look about how we're gonna do this. So in calculus 1, or likely, hopefully likely, you were probably introduced to the idea of the antiderivative. So this is not surprising. We say, oh, if we have a derivative, what function can we think of, what function might have that derivative? And we called that the antiderivative. So now we're going to basically rebrand that, and we're going to be calling really be thinking of that as the indefinite integral. So we notice that we're using the same symbol, the integral, but there's no limits on the integration here, and that is what we call the indefinite integral, and it represents an antiderivative of f. So if we say this, the integral, the indefinite integral of f of x dx, of little f of x dx, we say that is equal to some other function, capital F of x, with the understanding that this capital F of x, when I take its derivative, I will get back the little f of x. Okay, so we have to be a little bit careful with not confusing ourselves. One thing to be absolutely clear about is this right here is a function. It's not a number. So you notice that when we had the definite integral and we did the integration, we always got a number. Now we're doing the indefinite integral and we always get a function. So we have to be really careful about that distinction. One of them gives a number and the other one gives a function. Sometimes there can be a little bit of confusion about the notation, which is usually clear from the context, but sometimes when we are talking about the the indefinite integral, we are wanting to discuss the set of all functions, capital F, who have the property capital F prime equals little f, and sometimes we're talking about a single function. Now we're going to see coming soon that when we consider the set of all functions f, such that the derivative is little f, all these functions differ by a constant, but still we have to be careful. Sometimes we're talking about them all, and sometimes we're just talking about a single one. Okay, now the thing is, when we're doing the integration and trying to figure out what function has derivative, whatever the integrand is, there's going to be some that we're going to need to know, and we're going to need to know them on inspection. And the way that's going to be done is using our experience of differentiation. Okay, so those are listed here. All of these you should be able to do, so such that if you see something like this, the integral of sine x dx, you must then be able to say to yourself, oh yeah, which function was it that had derivative sine x? And then that should come into your head that was the cosine function, and then maybe you have to do an adjustment to make sure you get the sign right and stuff like that. But similarly here, maybe a better example, I ask what's the integral of secant squared. You need to be thinking to yourself, oh yeah, what function had the derivative secant squared? And then into your head is going to have to come is going to have to become this. Oh yes, I remember we went through the derivation of this. The derivative of the tangent is the secant squared. Okay, so some of them are going to need to be done by inspection. Those are listed for you here. Make sure that if you see any of the integrands here on the left hand side, and any of these ones here, that you will immediately be able to write down the right hand side. Okay, you see the left hand side, you're able to write that down without any thought. Okay, so they're listed here as we go along. You can refer back to this if required. Okay, the couple of these ones at the top are just, this is that you can factor out the constant. Here's that if you have a sum of two functions, you can split the integral up into two separate integrals, one for each of them. So there's a couple of little rules there at the top, but and those follow directly from the limit definitions. And then there's this table here of ones that you must be able to notice. Many of them, of course, as you can see, basically relate to the derivatives that we established of the exponential, the logarithmic, and the trigonometric functions. So that's where these are coming from. And then this one here is the power rule. Okay, you can always check. So that is an important point of integrating. Even when we get to doing more more difficult integrals, you can always check. Differentiation is an easy procedure, and you can take the derivative. So let us say, for example, let's take a look at this one right here. You're trying to integrate this, and you think that the answer is a to the x over log a plus a constant. So then what you can do is take the derivative of that. So I could take the derivative here of a to the x over log a, like that, plus c. And I go ahead with the differentiation procedure. I'm like, okay, so log of a is a constant. And then what is the derivative of a to the x? Well, that is log a to the x. And then there's that constant, log a. What is the derivative of a constant? That is 0. And then I simplify and I get a to the x. So then I have confirmed via differentiation that that statement is correct. So you can always do that. I encourage you, particularly on exams when you're being asked to find integrals, take the derivative, see if it works. It's a foolproof way of checking. If it does, you know you've got the right answer and you can just simply move on. Okay, there's a whole bunch of examples here. I'm going to go through them relatively slowly. If you feel already confident in your ability to do this, why not stop the video right now, integrate all these yourself, and then turn the video back on and check your work. That's better. If you already have the skill to do this, that is better than watching me do it. Okay, so let me start with A. Maybe I'll do it over here. A, the integral of x to the minus 2/3. So I am thinking to myself, what function has derivative x to the minus 2/3? So this is a power rule type of question. I'm thinking, okay, so I'm going to have to, when I differentiate, I will be subtracting 1. So then when I integrate, I'm going to have to add 1. So the first thing that occurs to me is that this should be x to the 1/3. Which I should write x to the 1/3. So I've added 1 to 2/3 and got 1/3. And then I think, okay, so when I take the derivative of x to the 1/3, I'm going to get 1/3 x to the minus 2/3. Well, that's what I want in the terms of the x to the minus 2/3, but I don't want a 1/3 out there in front. So then I'm going to put the 3 here. So then when I take the derivative, I get, let me see, 1/3 times 3, that is 1, and then I get x to the minus 2/3. That is correct. And then I'm not going to forget to add the constant, because the derivative of a constant is 0. So, and I'm going to find that when I, in many like in what we're going to end up calling initial value problems, where we're solving simple differential equations, you're going to need this constant to determine which of the family of functions is modeling the physical situation. It's important that we always put the constant in. Okay, so I can take the derivative. You guys are good at taking derivatives, so then take the derivative of this and make sure that you get that. Okay, let's do b. That would be the integral of t squared 3 minus 4t to the 5 dt. Okay, it's a product, which makes it look like it might be a little bit more difficult. If it was just some polynomial, a single polynomial, I would think that would be easy. So my idea of what to do here is to expand this to in this manner: 3t squared minus 4t to the 7 dt, and then it basically becomes two problems, just like the first problem above. So I'll just do that here. I'm thinking, what is the integral of 3t squared? Well, that would be t cubed. And then in my head, I'm just quickly differentiating. Yep, 3t squared. And then what function has derivative for t to the 7? So it's going to be t to the 8, and then I need a 4 out in front, so I'm going to put a half here, because when I take 8 times a half, I get the 4, and then I don't forget the constant. So then I've concluded which function it is for part B, and I can take the derivative, and then if I wanted to, I could factor out the t squared and make sure that it looks like that. Okay, similarly, question number C, the integral of u minus 1 u squared plus 3 du. I find it very easy to do this for polynomials. I'm going to, and when they're not factored, so I'm going to expand this polynomial, and I will get then u cubed plus 3u minus u squared minus 3 du. So I'm just expanding that polynomial, multiplying u times u squared and multiplying u times 3, multiplying minus 1 times u squared and minus 1 times 3. I get that integral then, and now I basically have 4 integrals that look like the one I've had the last 2 of. Okay, so expanding is sometimes very helpful. So let's go ahead and do this integral. That's going to be 1/4 u to the 4. That's the integral of u cubed. 3/2 u squared. That is the integral of 3u. In my head, I'm always just quickly taking the derivative. U squared, that's going to be 1/3 u cubed, and then the derivative of the integral of minus 3, that is going to be 3u, and then of course I have the constant. Okay, so I have my answer there. Now I can take the derivative of this, and I will get back to this, and then if I wanted to, I could divide u minus 1 into this thing here, u cubed plus 3u minus u squared minus 3, and I could confirm that I hadn't done anything wrong, and this would come out to u squared plus 3. If you do not know how to do this right here, polynomial long division, or you've forgotten or hoped that you would never see it again, let me encourage you to look up how to do that and practice, because we are going to come to an integration technique in a few lectures called partial fractions, and we are going to be wanting to be factoring polynomials, and one way that we're going to do that is using this polynomial long division. It's a highly useful skill. Make sure that you reclaim that skill if it is not currently in your repertoire. Okay, let's do D. D is the integral of 4e to the v minus secant squared v dv. Okay, so again, I'm going to do this in 2 pieces. What function gives me derivative for e to the v? Well, that is simply 4e to the v. And then what function gives me derivative secant squared? That is the tangent. So that if that hadn't occurred to you, you're looking back at that other list, reminding yourselves of the derivatives of the trigonometric functions, and then I have the constant. Okay, again, I'll check by differentiation. Okay, the last one here, looking a little bit more complicated, and this is in fact not the only way we could do this. If you had covered these and were doing them yourself, you may have done this one differently. I will do it in this manner here today, and then we'll have a similar question like this when we get to substitution, and you'll see that there's a different way of doing this as well. But what I'm going to do here is notice that 1 plus cos squared is sine squared. That reminds me, and I'm going to be doing this, so most certainly there's the trigonometric identities that you need to have at your fingertips, because you want, when you see something that you can simplify by using a trigonometric identity, you want it to occur to you to do that. And for me, the only way of doing that is to make sure that the basic ones are in my head. So just as a reminder, I mean, the most, for example, this one, sine squared z plus cos squared z equals 1. So most certainly you should recognize all flavors of that. And then what you can do to get two other related identities is you could look at this, and then you could divide the whole thing through by sine squared, like that. Just divide left and right side by sine squared, and then you would get 1 plus cotangent squared is equal to cosecant squared. Okay, so that gets you that other identity that you, at least for myself, I always do it this way because I can never remember, oh, is it 1 plus cosecant equals cotangent, or 1 plus cotangent, you can get yourself confused. So that's one way. And then you can take the same basic identity, that this one here, the sine squared plus cos squared z is equal to 1, is basically a statement of the Pythagorean theorem in the unit circle. So this is just Pythagoras in the unit circle. So then I can divide both of them by the cosine, like this. So I had 1 here, and then I'm going to divide by the cosine squared there. And that will allow me to get here the tangent squared. Tangent squared of z plus 1 equals secant squared. Okay, so then I get the 1 plus tan squared equals secant squared. So I get a sort of 3 for 1, and the 1, in fact, that I start with is just the Pythagorean theorem. Okay, long-winded thing of explaining why I replaced 1 minus cos squared with sine squared, and then I'm going to rewrite this in this way: cosine z, and now I have hang on a second here. I've got sine squared. I've got cosine. Nope, that's not what I wanted. I'm going to write it like this. Hang on a sec. Let's try again. I've got, now that I've sort of confused myself, let me write this out a little bit more in detail so I don't confuse you. Sine squared is sine z times sine z dz. Okay, now I am thinking about the fact that cosine over sine, this right here, is cotangent. And that 1 over sine, the other part here, is cosecant. And then I've got the dz. Okay, and then that allows me to recognize what this is. That is the derivative of cosecant, basically. So it's in fact, so again, let me put the detail of how I'm thinking here. Recall, so into my head becomes the trigonometric differentiation of the cosecant function, which I recall is minus cosecant times cotangent. So I'm looking at this, I see there's not a minus sign, so I have to compensate for that. And so the integral, the original integral that I was talking about, E, that is minus cosecant z plus a constant. Okay, so that last one a little bit trickier. We saw a few things. We saw the trig identity, and then remembering the derivatives of the basic 6 trigonometric functions. So you definitely should remember the derivatives of sine, cosine, tangent, secant, cosecant, and cotangent. All right, a little theorem here. We call this the net change theorem. If I take the integral from a to b of some function which is a derivative, then when I integrate it, I see that the value of this will be the function evaluated at the upper integral minus the function evaluated at the lower limit. This is basically allowing you to compute a change in say distance, a change in area, a change in elevation, like we're going to see right here. So we imagine a function, f of x, being the slope of a hiking trail, okay, at a distance x miles from the start of the trail. And then we ask, what does the integral from 2 to 4 of f of x dx represent? So the slope of a hiking trail, that means the rate of change of the elevation of the hiking trail. Okay, this means rate, derivative is always a rate of change. Rate of change of the elevation of the hiking trail. Okay. If the slope of a hiking trail is a large positive number, that means it's very tiring, right? It's a steep uphill. If the slope of a hiking trail is 0, that means it's flat. If the slope of a hiking trail is negative, that means you are going downhill. Okay, so this integral, when this integral here, when this f of x is the slope of my hiking trail, that is equal to the net change in elevation as you hike from 2 to 4 miles along the trail. Okay, so you're walking along a trail, you go from the mile 2 marker to the mile 4 marker, and you have an expression for the slope of the trail, and you take this integral, then you'll find out what is your net change in elevation. So let's just draw a graph to try to illustrate this with a couple of examples. Here's a graph. Here's your elevation. And I don't know, say this is here, this is your distance along the trail. And we're here at 2 miles. And then we're going to go over here to 4 miles. And let us just say that the elevation profile of our hiking trail looks something like this, like that. Okay, so little f of x is the slope. So here, for example, let's just pick something where I can draw it nicely. Let's say here at 2.5 miles, right here, this slope right here, that is little f of 2.5, because f is the slope of our hiking trail. Okay, so that you can see that changes as we're going along. It's the tangent line to the elevation profile. Okay, this number right here is f of 2, and then this number here is f of 4. Okay, and then the difference between those two, that is right here. That is f of 4 minus f of 2, and that's how much higher you are at mile 4 than you were at mile 2. Okay, so that is one illustration. This number can be 0. In fact, that would be like if your hiking trail looked like this, different hiking trail, and this would still be your elevation here, and this would still here be your distance on the trail. Okay, so the hiking trail could look like this. And you go up on top of something, and then you come back down on the trail like that as you're going along. This is not an up and back. This would be you're going up and over something and down the other side. So that would then be f of 2 would be here, and also so would f of 4. Okay, both f of 2 and f of 4 are at that line. Again, I mean, let me just pick some arbitrary position in here. Mile 3. At mile 3, this would be f of 3. Okay, so that's our slope. So we have that information, the slope information all the way along, and what we're trying to do is figure out how what is the net change in elevation. Okay, so in this case, despite the fact that you've gone up and come back down, your net change in elevation is 0. It does not mean that you didn't do any work and you didn't go up or down. It just means that at the end of the day, you're at the same elevation that you started at. So this is equal to 0. That would be, in this case, writing it in a different manner would be like saying it would be this here. There's been no change in your elevation from start to finish. The net change is 0. Okay? So now here's the thing that this is what my experience is easy to make a mistake about. And so if somebody says to you, oh, you went hiking and so you ended up at the same elevation that you started at, they say, oh, the trail was flat. No, the trail was not flat. It just means that your net change in elevation was 0. And if in fact you could go, I mean, in some extreme example, you could go and hike way up to a mountain peak, go over the top of the mountain peak and come all the way back down like that. And it would not be that you had, I mean, you would never say, I didn't do any uphill. That would be ridiculous. You have done a lot of uphill. So it's a different question if we were to ask, what is your complete amount of elevation gain? I mean, for that matter, you could have done something like this. You could have come back down and then gone up and then come back down like this. So sometimes, you'd want to know what is this change right here, plus maybe you also went uphill here too, so you'd want to know what is this change, and you would want to give an indication of that. Like in a hiking guidebook, you'd say, okay, so you're going to go up over the first peak and then down and up over the second peak. Total elevation that you're going to have to walk uphill might be, who knows, 4,000 feet or something like that. But at the end of the day, you're back at your car where you started from, and your net change is 0. Okay, so we're going to try to not mix up net change and then it's sort of a what we're going to call like a total increase, total amount of uphill walking. Okay, we're going to see this in a distance example, in a linear motion example coming right now. My experience, that's easy to make a mistake about. Okay, so let's now just talk about the linear motion of a particle. A particle is moving along a line with some sort of acceleration and an initial velocity. We want to find the velocity at time t. So it starts out at -4 meters per second, and it has an acceleration of 2t plus 3 meters per second squared, and we've got t between 0 and 3. And then we want to time the total distance. Well, okay, we've got a question here which we're going to be very careful about. We want to know what the distance traveled is. So we're going to make a distinction between the distance, the total distance traveled, how much did you go back and forth, and then the displacement, like, are you anywhere different than when you started on? So, we've got this particle, it's going like this, something like this, who knows? Could be going like this. We'll see what it's going when we could be going like this. Okay, let us just say we had a profile like that's all on one line. I just did it so you can see the back and forthness of it, but I'm imagining this whole thing being on one line. So just say our particle went like that, out and then back and then out and then back. Well, for total distance, what we would want to know is how long are all these little line segments added together. That would be the total distance traveled. For what we're going to call the displacement, we would want to know this distance. Okay, at the end of the day, how far are we from our starting position? Clearly, those are two big different numbers. In a non-COVID world, I wake up in the morning, I drive to SFU, I work, I drive back home. Clearly, I traveled some distance. In my case, probably about 60 kilometers total round trip. But at the end of the day, I'm back at my house, and my displacement is 0. Okay. Important distinction. Okay, so let's answer these questions here. What's the velocity at time t? So we know that the acceleration at time t is equal to 2t plus 3 meters per second squared. So the velocity at time t is the integral of the acceleration at time t. I mean, back in Calculus 1, you learned that the acceleration was the derivative of the velocity. So these are inverse functions. So this is how it works. So this is the Calculus 1 knowledge, which was this here. Okay. All right, so I can then now compute the velocity as the integral of the acceleration, which I've been told is 2t plus 3. I am integrating with respect to t. So then this is a simple integral, t squared plus 3t plus c. Do not forget this c, because we have an initial condition that the velocity at time 0 is minus 4. So what do we do with that? Well, we know the velocity at any time t is, I'm just going to rewrite it so we can see this here. The velocity at time t is t squared plus 3t plus c. So the velocity at time 0 is 0 squared plus 3 times 0 plus c. And that's equal to c. And then I'm told that the velocity at time 0 is minus 4 meters per second. That allows me to, what I would start saying, fix the constant. So, and what by fix I mean set it to a specific number. So I now have, in this problem, fixed the constant to minus 4. If when you integrate you leave out the plus c, you have no way of incorporating the information you have about the velocity at an initial time. So often called an initial condition, because we at time 0 when the clock starts, we're being told something. That's what we call that, an initial condition. So now in this case, then I have that v of t, the velocity at any time t is t squared plus 3t minus 4. Okay, that's answer to part A, the velocity at time t. Now, part B, the distance traveled. So we're going to be extra cautious about this, that distance traveled. Okay, there's sort of two possibilities. There's the net change in distance, and we will from here on out call that the displacement, called. And then there is the total distance traveled. Okay, so we're gonna take a look at how these things are different. So the displacement. Okay, so let's do that one first. One, displacement. The general case displacement, that is the integral from our starting time to our ending time of our velocity, and that is going to be whatever antiderivative we have of v of t. That is going, where I'm going to call that s, and it's going to be evaluated at t1 minus s at t2. That t1. That's our displacement. Okay, so right now we're, just so you know, we're going to be using a for acceleration. V is going to be velocity, and d is going to be displacement or distance, depending on the context. What am I saying? That's exactly what I wanted to avoid. S is going to be the displacement or distance. That's why I've used S. Why do we not use D, which is obviously tempting because D is the first letter? Because it's confusing then, because we often speak of the derivative of the displacement. And then what are we going to have? dd. This is going to be confusing. It's going to, so because d is now for us meaning, we're often writing stuff like this, d by dt. So d is taken on this meaning of the derivative. So we're no longer going to be using d for displacement or distance. We're going to use s. That's why I've used s here. Okay, so that's the displacement. And then 2, the total distance traveled. Total distance traveled is the integral from t1 to t2 of the absolute value of the velocity dt. So this is basically making the statement saying, well, okay, so we're going back and forth, but if I just imagine, if I take the absolute value and I imagine I'm always traveling in one direction, then I will get the total distance that I travel. It's like taking these lines here that I've got here and saying, okay, I'm going to count this one like that. And then for this guy here, I'm not going to put the negative sign on him. I'm going to extend this thing out over here And then this one's already in the positive direction. It's going to continue. And then this one is in the negative direction. I'm going to stick it out, keep going over here like that. Okay, so I use the absolute value to capture that idea of imagining that all of the travel is in one direction, and then that it all adds up properly, and I get the total. That's sort of a geometric look at why the absolute value signs are there. So absolute value signs are very important so that you get the correct result. So let us just look at an example of that. Still, we're not on the question we've been asked here, but we'll just take a quick example here, and that is I imagine my velocity here and my time here, and I imagine that my velocity is, here's t1, and I imagine my velocity to look like something like this. I'm headed out in the positive direction. My velocity is increasing, and then I slow down, then I turn around and I go back in the other direction, and I go like that, and then I stop here at time t2. Okay, I'm going to label this area here A1 and this area here A2. Okay, so the displacement is the integral from t1 to t2 of this velocity function here, and that is going to be a1 minus a2, and in fact it will be equal to 0 if a1 equals a2, which is kind of what I tried to draw roughly. I tried to make a1 look like roughly the same area as a2. So it'll be a1 minus a2, and that will be 0 if a1 equals a2. Okay, I'm thinking of those two things as areas. However, the distance that I go during this time will be the integral from t1 to t2 of the absolute value of v of t dt, and that will be a1 plus a2, and that will be equal to 2a1 if a1 is equal to a2 as intended in my drawing. So that's a big difference in the displacement. If we have this a velocity profile like this, the displacement is 0. I basically end up where I started from, but the distance traveled is not 0. Okay. All right, with this newfound insight, let us tackle the distance traveled for this part B of the problem. So what we're going to compute is part B, distance traveled, not displacement. Okay, so the distance is equal to the integral from 0 to 3. In this case, these are a timeline. We start at time 0 and we end at time 3, and then I'm going to take the absolute value of this function, t squared plus 3t minus 4 dt. Okay, so now we have to understand what parts of the interval, in what parts of the interval is this positive and which parts are negative. So to do that, I'm going to factor. So I'm going to write t squared plus 3t minus 4 in its factored form, which is going to be t plus 4 multiplied by t minus 1. And we are considering the interval between 0 and 3. So between 0 and 3, I'm then looking at this term here. Now t goes from 0 to 3, so that thing's always positive. Okay, so it's this guy that really matters. And that one is going to be negative when t is from 0 to 1. Okay, so I'm looking at that there, and I'm noticing that I can basically figure out that v of t is less than or equal to 0 when t is in the interval 0 to 1. And when t is in the interval 1 to 3, then I don't have to, I mean, the whole thing is positive. Okay, so that allows me to do this. The distance, I'm going to split the integral into 2. It's going to be the integral from 0 to 1. Now the velocity is negative at that time, so to take the absolute value, I put a negative sign there. absolute values. I think I mentioned this already. I possibly did just already once this course. Absolute value signs are critical. They don't go away, and they're tricky to deal with. So spend lots of time practicing. Okay, this little statement here is basically a statement of this sort of thing. The absolute value of -10 is, it's 10, but I'm thinking of that as negative 10. That's 10. Okay, that's why this negative is here, because I know that the velocity is negative. So in order to make it positive, I take the negative of it. Okay, and then in the interval between 1 and 3, the velocity is positive, so I can just remove the absolute value signs. Okay, that is the statement here. The absolute value of 10 is 10. I can just remove them. I've already got a positive quantity in there, and I just remove the absolute value signs. Okay, so that is that. I've now broken it into two integrals, and I've gotten rid of those pesky absolute value signs. And now this is a routine calculation, right? We've already integrated. We have two definite integrals, in fact, and they're polynomials. We've already had several examples of evaluating a polynomial, and we know how to evaluate that at the endpoints. So I am going to write a couple of the steps here and then give you the answer. Please check and do all the algebra yourself. So the first thing I'm going to do is I'm going to integrate. That's going to get 1/3 t cubed plus 3/2 t squared minus 4t evaluated at 0 and 1. And then I'm going to add to that 1/3 t cubed plus 3/2 t squared minus 4t evaluated at 1 and 3. Now it's an arithmetic problem, and I got out of this 13 over 3 plus 21 over 2. So now we're just here to here arithmetic. Make sure you can do it. Stop the video, go ahead and do it yourself. Make sure that you can do this. We will not be having any calculators or computers or such on our examination. It'll be like closed book with no calculator. So you want to be able to make sure that you can manipulate the small numbers that we'll be using effectively. Okay, this is 89 over 6 meters, and that is approximately 14.83 meters. So that is the total distance traveled. By contrast, let us take a look at the displacement. Okay, the displacement is simply the integral from 0 to 3 of the velocity, and that's the net change in distance, and that's going to be from 0 to 3. Notice there's no absolute value signs here, and we have to integrate the same function and evaluate it at 0 and 3. So of course we have the same antiderivative, and then we evaluate that at 0 and 3. Evaluated at 0 and 3, arithmetic problem, and that comes out to be 10.5 meters approximately. 10.5 meters. What example did I actually got, that's not approximately, it doesn't look like, in fact. No, it's not approximate, because the exact one was 21 over 2 meters. Okay, so what do we notice? We notice that the distance traveled is bigger than the displacement, and that is always the case. Okay, so it is always the case, always the distance traveled is greater than or equal to the displacement. Okay, so that is the net change theorem with a couple of applications. All right, that concludes section 5.4 on the indefinite integral. See you again for section 5.5. Thank you.